Welcome to our session. As Igor mentioned in Slack, today we're going to talk about a very important topic, binary search. Before we start binary search, let's do much easier problem. Let's just do a regular search in array. So let me share my screen. I am sharing my screen now. Do you see my screen? Cool, thanks. Let's go. We covered recursion last time, which gives us an ability to cover lots of different algorithms because many of them are using recursion. Previous lesson, we showed you very simple recursion problems, and those problems were actually more efficient to solve with the iterative approach. So recursion made just worse complexity. However, we will slowly see the power of recursion starting today. Let me create a new class. Research. Apple, Facebook, and other big companies love to ask this question because it's really beautiful problem, I would say. Great. As I mentioned, let's do just a regular search before. So the problem statement is give an array of integers and target is find the location of target. So, for example, if you are given with something like that, 2, and target equals to 19. So what is the location of target? That's a question to you. Five. 0, 1, 2, 3, 4, 5. Good. So by saying the location of target, we just mean what is the index of corresponding integer. And how could we find this location? Obviously, if we don't know, we know nothing about the array. We don't know what is the sequence of the elements inside. We don't know the minimum and maximum element. There are not much options here, right? If we need to find this target, we would definitely need to go through all of them and check if the new number is our target, right? There is no probably other way to go. However, sorry, let's just do this for now. So I'll create public. So I need to return, well, let's copy our 8 rules. Here it is. So great. So input, what is the input parameter? Obviously, we are given with array and the target itself, which means we are going to have something like a search, an element, and your arguments will be an array of integers, right? And the target, which is integer as well. Now, what is return type? What is your output? You need to find the index of the target inside the array. Your index is obviously an integer as well, so we can easily say that we are going to return int here. Cool. So we talked about that we know nothing about the array, so there are not much options. The only way to go is just to iterate through all of them and compare every new element with the target we are looking for. And if they match, that's our answer. So I would use for each loop, right? So for, let's say, element array, and to do that, you just need to use parentheses, right? What's wrong here? For, didn't use Java for each for a while. Array is what do you want from me? Do I need to use for each? For, oh, I see, element, of course, int element, right? Obviously. Yes. Thank you, guys. So our array is integer array, means our element, every new element inside the array will definitely be an integer. So you have to specify this in Java. Now, if the element equals to the target, then you found it. Actually, sorry guys, for each is not enough here, right? We need an index to return. So let's just move everything, but just use regular for, right? For int I equals 0, where we want to iterate I before length, and every step will be I++, incrementing by 1. Now, if array from I equals target, then that's our answer. And the return, we should return I. Cool. If we went through the whole cycle and we didn't find such an element, the problem statement usually should tell you what to do. It should either tell you, assume the array contains target, something like that. Then you can definitely be sure that it contains target, or it will say, if there is no such an element, please return -1. So if this edge case is not specified in your problem statement, feel free to ask the interviewer. That's a good question to ask. In our case, let's say return -1. So if we didn't find such an array, such an I, where array from I equals target, and we did not return here, then we can return -1. Cool. Quick unit test, binary search. And that's not binary search, that's just a regular search. Binary search tests. Search and element test. What do we have here? We have array, right? We usually say that we have expected result. Sorry, how do we do it? We have array, we have target, yes, of course, and then we have expected result. So let's say we have 10 minus 100, 7, 19, 9, 10, and 5. And we are looking for target, which is, let's say, minus 100. Then expected result will be 1, right? 0, 1. Then we can create the binary search object. After that, we can say int actual result equals binary search dot search an element. And your arguments will be your array, which we created right here, and the target, which we created here. Then we can just say assert equals expected result with actual result. Perfect. Let's quickly run it. One test is enough here because it's an extremely simple problem. Good. Now, we have our array. Let's go back to our problem. What is runtime complexity here, first of all? Please select me your thoughts. Should be straightforward, right? What is runtime complexity? Right. So time is definitely big O from n, where n is the size of an array. And memory, what's about memory? Constant, correct. We didn't use any additional memory here, so we're good to go. But runtime complexity is big O from n. Now, let's modify our problem statement a little bit. The only difference inside our new problem will be the array is sorted. What if array is sorted? In the first view, nothing changes, right? We still have an array, and we need to find some element inside. So let's just use same array, but sorted. Basically 2, easier to write, 2, 3, 6, 19, 10, 19, 100, and the first one is minus 39, like that. Minus 39, 2, 3, 6, 10, 19, 100, correct? Looks good. And the target is 19, right? So the new expected result is what? What is the allocation of our new target? Five again, right? That's funny. 0, 1, 2, 3, 4, 5. Yes. So in the new index is 5 again. On the one hand, nothing changes. We still have an array. We have a target. We know that we somehow have to. We need to go through all of them to find the correct one. But that's not true. So any ideas? What can we do to find our 19 more efficient? Using a midpoint binary search. Yes, if you know the binary search, that's obviously um, a, a good optimization for the search. So let's slowly try to see what's going on inside. Basically, the idea of binary search is powerful and simple. What if we know that the array is sorted? What if we check out the midpoint? The midpoint inside this array. Let's say it's 6. Now, we know that array is sorted. Means if we are looking for 19 and we took a look here and we know it's 6, then obviously we know that 19 is bigger than 6, means our target is in the right part of what we just looked up. So if we looked up in the middle and we see 6, we know exactly that we can cut off the whole left part of the array. And that's half of the all elements already. And we know that we don't need to look through them because 19 will never be here if the array is sorted. So array is sorted is powerful addition that gives us this ability to do this trick. Cool. Now, once we found that our 19 is the right part, let's write it down, right? So mid element equals 6. Then 19 is greater than 6. As a conclusion, we can assume that target is in the right part. Means we can do the same operation inside the right part only. So the new array, and obviously we compare the 6 with the target itself first, because if the 6 is a target, then we found the solution. We don't need to do anything else, right? We found it already. It means the new array is from 6, actually from 10, because 6 is checked already, right? So from 10 to 19 and 100. That's our new array. Let's do the same sequence of steps. Let's find the mid element. 19. In our case, that's a target. Equals target, found. Right? But the idea is let's divide and conquer. It's called divide and conquer, right? We have this big array. In our case, it's not that big, but in real life, it can be huge. Let's just divide and check out the middle element. What if the mid element equals to our target, or it's less than our target, or it's greater than our target? If it is a target, we found a solution already. If it is smaller than our target, then we know that our result is in the right part. If it's bigger than our target, we know exactly that it's inside the left part. That's an idea. How to code it? Let's start from input. what is an input here? Obviously, same input as in our search environment. The only difference is the array is sorted. So I'll just say public int because we are still looking for integer index to return. Binary search. And the arguments are actually same. What are the arguments? Array, and target. And target, great. Now, as I mentioned already, we have to somehow find the mid element. How to do that, by the way? If we don't know what is the mid element, right? We are looking for this 6, but how to find it? You probably cannot use the array dot size divided, right? Why? Because actually we don't know where are we operating on this array. If we are operating on the right size only, we need to somehow specify that we are operating from this index to this index. And obviously one idea is to create a new array every time, but that's definitely a bad idea. Firstly, you spend a lot of memory. Secondly, it's really even more complicated to do that. So it's easier to pass as an argument the left index and the right index. And for the first iteration, your left will be 0 and the right will be array.max. But as deeper you go inside the recursion, because why do we need recursion here? Because we basically need to return the same sequence again and again, right? But the problem statement is smaller. That's perfect case for recursion, right? So we are going to call the same function again and again, providing it the bounders to operate on the array. Means if we have binary search array, let's not modify this syntax. Let's just create another function and we'll call this function from here. So same thing, int, I'll name it binary search recursion. And the arguments here will be obviously an array. Obviously target. But very important new part of the argument sequence will be left and right bounders. So let's say L and R. Again, what do they mean? The array will be always the same, the one the program statement provided. But once we cut off the left part, let's say, of array, we need to somehow specify that the array is same, but we assume there is no left part. So the left boundary will be in the middle and the right boundary will be there. Then you repeat same thing with the right part, and let's say you split it to the half and operate only with the left part. Then you say that your left boundary is this index and your right boundary is this index. Something like that. So now, using left and right, let's find what is the middle of those. So how to find the middle between left and right? Right. So let's say left is 100 and the right is 200. The middle between them obviously is 150, which is 100 plus 200 divided by 2. Similar to the average between those two boundaries, right? So let's say middle equals to the left plus right divided by 2. This is a middle index though, right? Index, not an element in itself. Do not forget this. So this is not a 6. It will give us the index of 6, which is 0, 1, 2, 3. The middle index will be 3 right now. Good. Now, what to check? We have 3 different options here. The first one is the easiest one. What if our element is actually found or is already found? So basically, what if our element, middle element, is our target? In that case, if array from middle index, if it equals to the target, then the problem is done, right? It's the easiest case. Then we can return middle index because we are looking for location, right? As a result, and if we found the index where the element, corresponding element equals to target, then this index is our answer. Pretty fun. Now we have other 2 cases. First one, if our what? If our target is less than array from middle index. So let's assume we were looking for minus 39 and we splitted the array. We looked up for 6 and we see that our minus 39 is less than 6. So target, oh, sorry, that's vice versa. Our example is perfect case here. So our target is 19. We splitted the array and we are looking for 6. We look up 6 and we compare it with 19. And we see that 19 is greater than 6. 19 is greater than... What's going on? Sorry, guys. Target less than array from middle. So target, let's say 6 is... Oh, target is 19. Yes, sorry, I completely messed up everything. Let's just read whatever is written already. Target, which is, let's say, minus 39. And if minus 39 is less than our 6, that is a case. Then we know that we need to look up in the left part, and we can omit the right part. What to do in that case? We know that we have left boundary and right boundary. And if we see that our target is in the left part, then we need to move right boundary, right? So because it was a left boundary, it was a right boundary. We know that the target is somewhere here, then we need to move right boundary from here to here. Basically, new right, new R equals, we already looked up 6, so we should move it to this element, to 3. And this is middle index minus 1, right? Because middle index is 6, we looked up it already right here, so we don't need to use it once again. We can just say that let's start from here down. And obviously we need to call recursively the same function, right? The difference will be the boundary will be more narrow, which gives us a smaller problem, which gives us confidence that sooner or later recursion will end. It will not be an infinite. What are the arguments here? The array is the same, obviously. The target is the same. The left boundary is the same. The only difference is new r, which is middle index minus 1. Now, important thing. We are writing a recursive function that returns something. It returns the integer in our case, right? So basically, right here, we have to say that at this moment, we need to return whatever will be returned here. So this is a deep recursion, right? It will return whatever will be returned here. At some point, deeper and deeper and deeper in recursion, this condition should be true, and it will return the correct index. Then it will go up, up, and up again, and finally return the middle index from somewhere deeper level at this point. Else, if the target is greater than array middle index, right? If target is 19 and we found 6, then right boundary is fine. We need to move left boundary. To do that, we can say that new L, new left, is middle index plus 1. Same logic. We double checked 6 already, so we can start from 10 now. And the 10 has an index, middle index plus 1. Now we need to return binary search recursion array target UL and right. Cool. Now, as every recursion, we should have a base case. In our case, this is a part of base case, obviously, right? If we finally found an element. But what if we are not able to find the element? Then how to end the recursion? Let me draw. So this is our array. 0, 1, 2, 3, 4, 5, 6, and 7. We know that our mid index is 0 plus 7 divided by 2 is 3. So we look up here. Let's say we compare to our target and we are able to find that our target is somewhere in the right part. Then we split this, no more this, right? And then we move left boundary from here to here, right? Then let's say we split again, we look up here, and we are able to say that our element is less than the fifth element. Then we move right boundary here. Then we split, left is 4 and right is 4 at this moment, right? Left is 4 and right is 4. We don't really need to manage floats, because when you divide like that, that's a whole division, remember? So let's say if you have 0 and 7, it will be 0 plus 7, 7, divide by 2. This will give you not 3.5, it will give you a 3, because this is an int, and left is int and right is int. Integer division gives you an integer, not a double. So right now left is 4 and right is 4. We do it again. Left 4 plus 4 is 8, divided by 2 is 4, of course. We do the same thing, but let's say we can't find target. So we understand that left, let's say, should be moved to the right. So we move left somewhere here, and we have the situation that right is 4 and left is 5, which means there is no such element, right? Because left went through the right. That's our base stop. So if our right is less than left, then we can return -1 or whatever the interviewer will ask you to return. Questions at this moment? Any questions? If everything is clear, please provide plus, so I can see that we're all good. Great. This is really, really popular topic on the interview. So many of our graduate students got this problem. Great. Okay, crystal clear. Perfect. Now, how to call this recursion function from the binary search? Obviously, we need to say binary search recursion, pass the array that will be passed here, pass the target that will be passed here. But now, left and right, the caller side doesn't need to know that our implementation requires left and right. So the caller side will just pass array and target, and internally we will return binary search recursion, array target, then the left boundary will be 0, right? The left boundary is 0. And the right boundary is, what is our right boundary, guys? Exactly. We know the index of the last element. That's our right boundary. So our right boundary will be array.length -1. Let's do some unit tests. So let's say binary search test equals -100, 5, 7, 9, 10, 19, and let's right minus 105. Actually, we don't need to do same array, right? We can say 123 and 10,000, and that doesn't really matter. The only important thing, it should be sorted, right? Otherwise, binary search does not work. So array, let's say target equals to 123. Expected result will be 0, 1, 2, 3, 4, 5, 6. What if that? So let's create binary search, then use binary search here, and there was a search, expected result with an actual result. So let's double check. Everything passed. There are more important tests that I would like to see at the interviewer if I asked to write this. Let's say binary search, let's say or binary search test 2, whatever. Let's ask to find -1 or -90, something that does not exist. So expected result will be -1 here because this element does not exist here, right? Let's double check. And we found it as well. Then the last one good will be, what if it's -100? Then I would expect 0 as a result. And that's exactly what can we see here. Great. So again, binary search, really important and powerful algorithm. I would recommend you to rewrite it with iterative approach at the homework, because you can do this with an iterative approach without a recursion. Really. The idea is very similar, so feel free to write it and feel free to Slack in the general channel your solutions. Any other questions about binary search? Hopefully all is clear. Great. Complexity, very good. Very good. Complexity. Write unit test done. Runtime complexity and memory complexity. So who does know the complexity of binary search? We know that the regular search takes big O from M. What is the complexity of binary search? Exactly. This is logarithmic complexity. So time here is big O from log M. What does it mean? And memory is constant, right? We didn't use anything, right? So what does mean log n and why it's log n? Because as you can see, we split the array by 2 every time. So let's say the size of array is n by default. Then we split it by half. Then we split what's left by half. Then we split by what's left by half. So the maximum number of operations here is how many times we can split the n by 2. So n divided by 2, divided by 2, divided by 2. In the worst case scenario, we are unlucky and we compare every time the middle element with the target, and we are not able to find it. So we divide, and the worst case scenario, we just see the last element and it's our target. So how many times can we divide n by 2? That's exactly log n, because log n shows you what is the power you need to raise 2 to get the n. So 2 to the power of this number, it will be n. That's exactly what we need. And this is very good complexity. To compare the log, let me show you. Log. So to compare, if you will try to find the log of, let's say, 1 million, it's basically how many times you need to calculate, you need to do, let's say, 1 million, huge number, right? With our first approach, you will need 1 million operations here. But here, you need to just divide by 2, then divide by 2, that's second, then divide by 2, that's third, then divide by 2, that's fifth, then divide by 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, we have 3 elements left already, 20. Then we have 1 element left. So in the worst case scenario, if we are very unlucky, we will be able to find it within 20 operations if we have 1 million elements, which is great complexity, right? In this case, we will need 1 million elements in the worst case scenario. So this is a pretty powerful complexity. Good. Any other questions?